Hello students, welcome back to the lecture series on discrete mathematics. We are learning binary relation and this is video part 3. In the previous session we have learned the types of binary relations, and in this lecture we are going to see what is equivalence relation and partial order relation. So the definition: a relation R on a set A is called an equivalence relation if it is reflexive, symmetric and transitive. Now consider the following relation defined on the set. A is a set containing 3 elements, namely 1, 2 and 3, and the relation R is given. First of all, to see whether the given relation is an equivalence relation, we should be able to prove that the relation is reflexive, symmetric as well as transitive. So let us check for the reflexivity. Since A contains 3 elements 1, 2 and 3, each element of the set A should be related to itself. That means we should have the pair 1, 1, 2, 2 and 3, 3 in the relation, which is there. Now for any A related to B, we should have B also related to A. Let us check for such pairs. We have 1, 2, 2, 1, 3, 4, 4, 3, 2, 3, 3, 2, 1, 3, 3, 1. So for each pair A related to B, we also have B related to A, and the relation is a symmetric one. For transitivity, we should check if A is related to B and B is related to C, we should have A related to C. So if you check 3 is related to 3 and then 3 is related to 4, we should have 3 related to 4, which is there. Then 4 is related to 3, 2 is and 3 is related to 2. So we can see that 4-2 pair is not there. So this relation is not equivalence relation. Now let us see the examples which are equivalence relation. First one is equal to on a set of real numbers. You may consider any set of numbers, maybe natural number, or it is also true for the set of integers. Since A equal to A for all the numbers, all the real numbers, this is reflexive. If A equal to B, then B is also equal to A, therefore the relation is symmetric. And the transitivity is A equal to B, and if B is equal to C, then we may conclude that A is equal to C. So this is an example of equivalence relation on set of real numbers. Example number 2 is less than or equal to. So let us check for the reflexivity. A is less equal A for all the real numbers. So reflexive condition is satisfied. Now symmetric. Since equality is there, we may say that A less equal B and B less equal A. For transitivity, if a number A is less equal B and the number B is less equal C, then we have A less than or equal to C. So the transitive condition is also satisfied, and therefore the example number 2 is an example of equivalence relation. The next is partial order relation. Now let us see the definition first. A relation R on a set A is said to be partial order relation if it is reflexive, antisymmetric and transitive. Antisymmetric definition and the concept we have learned in the previous video. The example number 1 is subset of is a partial order relation. Since reflexivity is justified, since a subset A is always a subset of itself. A is subset of A for all the sets. Antisymmetric. If we have the condition A is subset of B and B is subset of A, then obviously A is equal to B, because that condition is true only if the two sets are equal. Transitivity. If A is a subset of B, that means A is contained in B, and if B is contained in some other set C, then obviously A is a subset of the third set, which is C. So transitivity is done. So the example number 1 is reflexive, antisymmetric as well as transitive. In the example number 2, on a set of positive integers, I'll tell you why I have taken the positive integers, because if you consider all the real numbers or uh, negative integers as well, this is not a partial order relation. First is check for the reflexivity. A divides A. For each number, the number divides itself. So reflexivity is done. For antisymmetry, if A divides B and B divides A, since we all have the positive integers, we don't have the case like 2 divides minus 2 and minus 2 divides 2, but 2 is not equal to 2. In that case, it is not an antisymmetric relation and it won't be a partial order relation anymore. So, but if you are considering only the positive integers, the is divisor of this relation is antisymmetric, because we are considering the only the positive numbers. So 2 divides 2 and then 2 divides 2 and 2 equal to 2. The transitivity is also there. A divides B, and if B divides C, A will be a divisor of the number C, and therefore transitivity is done, and example number 2 is a partial order relation. Now example 3 is less than or equal to. Less than or equal to is first one reflexive, since A less equal A. The next is the antisymmetry. We have A less equal B, and if B less equal A, then obviously A is equal to B. The transitivity is done. We have seen this in the previous one also, where we were checking for the equivalence relation, that this is transitive. A less equal B, B less equal C, so obviously A less equal B. So this way we have completed with our types of the relation and the equivalence relation and partial order relation. Thank you.